Okay, so chapter 6 is basically about the normal distribution. So what is the normal distribution? Normal distribution is a symmetric mound-shaped distribution that has a tail going off in both directions, and a lot of different data that comes up naturally kind of fits this pattern, fits this distribution. For example, if we look at the heights of animals, whether it's animals or humans, most of the data is clustered around the center, around the average, with a little bit of data coming out in this tail and a little bit of data coming down in this tail. So this is an example of some female heights that follow a normal distribution. But you also see this same shape when you look at almost any measure of intelligence. For example, you look at SAT scores, the majority of SAT scores are within a couple hundred points of average, and you have a few unusually high scores over here and a few unusually low scores down there. Even if we look at something like coin flips, I did this little simulation on Excel where I'm flipping a coin 20 times and I'm counting the number of heads, and then I'm looking at how often did I get 0 heads, how often did I get 1 head, how often did I get 9 heads, how often did I get 10 heads, etc. And then I graph the results, and the graph of those results once again looks like this normal distribution with the big clump of data in the center and a little tail going in this direction, a little tail going in that direction. So the normal distribution is symmetric, therefore the mean is equal to the median. It's mound-shaped, it's unimodal, meaning it has one mode or one peak, and it has two tails. And this picture is referred to as the empirical rule. Any data that follows a normal distribution, 68% of the data will be within 1 standard deviation of the mean. So that's from 1 standard deviation below the mean to 1 standard deviation above the mean. So if we're talking about the height of females, 68% are within 1 standard deviation of the mean. If you're talking about SAT scores, 68% are within 1 standard deviation of the mean. The other interesting thing about the 1 standard deviation mark on the curve is the 1 standard deviation mark is where the curvature changes. So this center part of the curve here, the curve is concave down. Over here, past the 1 standard deviation mark, the curve is concave up, and over here the curve is concave up. So it just so happens to be that the 1 standard deviation mark is where the curve changes from concave up to concave down and vice versa. Also, this 1 standard deviation mark, when you go up to the curve, that occurs at about 60% of the overall highest point of the curve. If you go 2 standard deviations on either side of the mean, so that's the mean minus 2 standard deviations to the mean plus 2 standard deviations, that encompasses 95% of the data in a normal distribution. So if it's female heights that follow a normal distribution, 95% of them are within 2 standard deviations of the mean. If we're talking about SAT scores, 95% of SAT scores are within 2 standard deviations of the mean. If we use the symmetry of the normal curve, I know this picture looks a little bit messy, but if we use the symmetry of the normal curve, we can say that the 68% is split up into 2 different pieces that are each 34%, and the 95% is split up into 2 pieces that are each 47.5%, and so on with the 99.7%. And then also, if from here to here is 47.5, and from here to here is 34, then that means from here to here has to be 13.5%. So some classes where they don't make extensive use of technology, they have students memorize this diagram, but that's not really necessary. The biggest thing that you need to know from this diagram is that 95% of the data is within 2 standard. On most of these problems with the normal distribution, we're going to be turning some raw data into a z-score. And the reason for that is we're going to use one table in the book that will work for any data as long as it's normal. So if it's data on people's heights, if those heights follow normal distribution, we get to use this table. If it's SAT scores and they follow a normal distribution, we get to use the same table. Even though the numbers representing people's heights are completely different than the numbers representing SAT scores, we can use the same table for all normal situations by turning our data into a z-score. So here's an example of doing that. The heights of adult males in the U.S. follow a normal distribution with a mean of 69 inches and a standard deviation of 3 inches. What percent of adult males in the U.S. are shorter than 62.2 inches? So the first thing we need to do is turn that 62.2 inches into a z-score. So the 62.2 inches minus the mean divided by the standard deviation, pretty simple little arithmetic problem. And we get a z-score of negative 2.27. So the fact that the numerator is negative 6.8, that simply means that someone who is 62.2 inches tall is 6.8 inches below the mean. But the z-score of negative 2.27 means that this height is 2.27 standard deviations below the mean. And that's what we want to do on all of these problems, is we're usually turning things into standard deviation units. How many standard deviations above or below the mean is a certain value? So now this z-score of negative 2.27, we're going to look up on a table. The table, by the way, is on the class web page. If I can go over there on the class web page. On the class web page, if you click on tables and then scroll down a little bit, you'll get to the standard normal table. Also, on the homework problems, there's a link to this table. Okay, so let me zoom in here a little bit on how we're looking at this table. So we have a z-score of negative 2.27. We've got a z-score of negative 2.27. So right here is our negative 2.2. And since it's negative 2.27, we come to this column here with the 0.07. And the number right there on the table is 0.0116. So getting us to the negative 2.2 tells us what row to be on, and the 07 part of that z-score tells us what column to be on. So when we look up the negative 2.2 over here and the 07 over here, that's our z-score. And this right here is the proportion or the probability that we're looking for, 0.0116. If our z-score had been negative 2.26, then our answer would have been 1.19. Sorry, 0.0119. If our z-score would have been negative 2.25, our answer would have been 0.0122. So, also if you notice the picture or drawing at the top of this table, this is just a reminder that this decimal number, this proportion you're getting off of the table, is the proportion of the normal distribution that is below the z-score you're looking up. Okay, so the proportion of the normal curve that's below a z-score of negative 2.27 is 0.116. And oftentimes we write it like this. It looks like probability notation. First, in terms of the raw data, a person's height x being less than 62.2 inches, and then a z-score being less than negative 2.27, because that's what we got when we turned this height into a z-score, and then this probability or proportion from the table. If you want to write this as 1.16%, that's fine, but usually it's okay to just leave it in the decimal form that you get off of the table. Here is an illustration of that 1.16% on the calculator. Here's the normal curve, and here's a little tail area here that comes out to be 0.0116. Okay, before I continue with a slightly different example, the way you can get this off of the graphing calculator, if you have such a machine, second vars, and the second item on the list is NormalCDF, and by default it says -1E99, which is scientific notation. That's basically the biggest negative number the calculator can hold, so that's kind of like saying negative infinity. And then for the upper, our z-score was -2.27. And we always leave the mean as 0 and the standard deviation as 1 if our -2.27 is a z-score. And this should give us the same 0.116 number that we got off of the table. So you can use technology or use the table, but they've already been calculated for us on the table, and you're going to be able to use the table. So there we have it. So now here's a slightly different example. What proportion of adult males in the U.S. are shorter than 72.9 inches? Well, let's turn the 72.9 into a z-score. When we turn that into a z-score by subtracting the mean and dividing by the standard deviation, we get a z-score of 1.3. So someone who is an adult male who is 72.9 inches tall is 1.3 standard deviations above the mean. So we go to the table again. This is a second page of the table which has positive z-scores, the row for 1.3 and the column for 0, 0 because it's 1.3 exactly. And then we get that decimal number there off of the table, which is 9012. So the probability of an adult male being less than 72.9 inches is the probability of a z-score being less than 1.3, which is 0.9032. If we do greater than, that presents a little bit of a twist. What proportion of adult males in the U.S. are taller than 73.1 inches? So we turn the 73.1 inches into a z-score. Then subtract the mean and divide by the standard deviation, and we get a z-score of 1.37. And we look up 1.37 on the table. So there's 1.37. And the number on the table is 0.9147, but that's not our answer, because remember that the number we get off of the table is the proportion of the curve that's below our z-score, but in this case, we want the proportion that are taller than 73.1 inches, so we're going to have to do 1 minus the number that we get off of the table. So the number we saw on the table, we're going to do 1 minus that, so 1 minus the 0.9147, and that gives us 0.085. Then another situation that comes up often is to find the proportion of the normal distribution that's between two values. So what proportion of adult males in the U.S. are between 70.77 inches and 71.88 inches? So now we have two different heights that we have to turn into z-scores, and these are the two z-scores. And then we're going to look up both of those z-scores on the table. And so I have them highlighted here. Here's the 0.59. Here's the 0.96. And when we get those 4-digit numbers off the table, we're going to subtract them. So in probability notation, it would look like this. The probability of a man's height being between 70.77 inches and 71.88 inches is the probability of a z-score being between 0.59 and 0.96. We look at the 0.96, that's 8315. We look at the 0.59, that's 0.7224. Subtract those two, and we get 1091. Really common mistake when students are first learning about this is that they'll subtract the z-scores. We basically never subtract z-scores. We look up the z-scores on the table, and then the 4-digit numbers we get off of the table, we subtract. So a recap of what we've done so far is we take the raw data from the problem and convert it into a z-score by subtracting the mean and dividing by the standard deviation. And then we look up that z-score on the table. If the problem is less than, then the number off of the table is our answer. Done deal. If the problem says greater than, then we're going to do 1 minus the number we get off of the table, and that'll be our answer. If the problem says between, then we're looking up two z-scores and looking them both on the table and then subtracting the numbers that we get off of the table. Okay, now let's do a problem where we do all of that backwards. What adult male height represents the 95th percentile of adult male heights in the U.S.? This problem is backwards because every other problem we started with a height and ended up with a proportion or a percentage. On this problem, we're starting off with a percentage, the 95th percentile, and we're going to have to turn that into a height. So 95th percentile means that 95% of the data is below you, so we first need to figure out what z-score has 95% of the normal curve below it. So this is kind of using the table inside out. And right in here is the closest you're going to find in the interior of the table to getting 0.95 exactly. So this corresponds to a z-score of either 1.64 or 1.65. And it doesn't really matter to me which of those that you use. If we use the calculator, we would get a more precise 1.64485 answer, but either 1.64 or 1.65 is just fine. So now we know that the z-score should be about 1.64. Now we have to use the z-score formula backwards. We know the z-score, 1.64. We know that the mean of all male heights is still 69 and the standard deviation is 3, but we don't know the exact male height that corresponds to the 95th percentile. If we can solve this problem backwards, we'll have the adult male height, which is 73.92 inches. So a couple steps of algebra here, and we get 73.92. But the formula on the formula sheet, they've already solved the formula, the z-score formula for x. So we can use that from the formula sheet without having to do any algebra. It's just mu plus z sigma. So the mean 69 plus our z-score 1.64 times the standard deviation of 3. So if we used a z of 1.64, then we get 73.92. If we use a z-score of 1.65, then we get a height of 73.95 inches. If we use a z-score of 1.645, then we get a height of 73.935 inches. So either way, we're getting about 73.9 inches. So any of those answers should be marked correct. If you do something cuckoo like use 1.6 as your z-score, then we're going to have a bit of a problem. Let me go back and show you how to do some of these earlier problems with the calculator again. So we turned 72.9 inches into a z-score of 1.3. On the calculator, that would be second bars, NormalCDF, and our z-score is 1.3. And there's our 9032, which is the same answer we got off of the table right here. If we're going to do greater than, if we're doing it on the calculator, then we don't necessarily have to do that 1 minus operation. To do this greater than problem on the calculator, we again do second vars NormalCDF. But now my starting point will be 1.37, and my ending point will be infinity. So greater than 1.37 is going to be from 1.37 to infinity. And for infinity, you just put in any kind of big number. And there's 0.853, which is exactly what we got by doing the 1 minus operation from the table. And if we have a between problem like this one on the calculator, we got a z-score of 0.59 and a z-score of 0.96, then we can say second vars NormalCDF, 0.59 and 0.96. And this should give us the same answer, 1091, that we got over here when we subtracted the numbers we got from the table. So let's go look at how all of this plays out on a couple problems from the homework. So the early problems on the homework already have z-scores. So they're already talking in terms of z-scores. So this would be the area less than a z-score of negative 1.92. So if I can find negative 1.92 on the table, negative 1.92, that answer should be 0.274. And then let's see, the next one, greater than 1.03. So we look up 1.03 on the table. 1.03 is right here. That's 8485. And I'm going to have to do 1 minus 8485. So 1515. And then this one is in between, so I got to look up two different z-scores on the table. I got to look up a z-score of negative 0.65. So negative 0.65 takes me to right here, 2578. So 2578. And then the other z-score is negative 1.76. So negative 1.76. Negative 1.76 takes me to here, which is 0.392. And subtract, and I get 2186. And the last problem here. Oh, now we're going two different directions. So we got to do less than negative 0.26. So negative 0.26. Negative 0.26 is right here, 3974. And then we're going to add to that this area over here, which is greater than 1.98. So if I look up a z-score of 1.98, that's 9761. But the area greater than that is going to be 1 minus 9761. So I'm going to do parentheses and then 1 minus 9761. So that answer should be 4213. Let's try that and see if we got any of these right. Okay. So these all look all right. Like I said, most of these early problems, they already are in terms of z-scores, to the left of a certain z-score, to the right of a certain z-score, in between a couple of z-scores. They have some problems where you have to go backwards. So find the z-score. Let me do a different one that's backwards. So find the z-score for which the area to the right is 0.5. 0.14. If the area to the right is 0.14, then the area to the left is 0.86. 1 minus 0.14. So 0.86, let's go back to our normal curve, and our normal table, I should say, and we're looking for 0.86. And right here, that's the closest we're going to get to 0.86, 0.8599. And the z-score that corresponds to is 1.08. So, I don't know why that, okay, 1.086. So I think the z-score we want there is 1.08. Check that answer. Okay, so that's what they're looking for. And then you get about halfway through this assignment, and you start getting word problems. So now they're going to give us the mean, and they're going to give us a standard deviation, and they say what proportion of the population is between 20 and 30. You're going to have to turn both of these numbers into z-scores and then look up both of those z-scores on the table, and so on. So all the rest of these problems are similar to the early problems, but they're just in terms of z-scores. Well, that about does it. So email me with any questions, please, and hope you have a good spring break.